Hello and welcome to the LeetCode Larry Show. I am your host, LeetCode Larry, the only guy on the planet named LeetCode Larry whose name is not actually Larry. And today we're going to be looking at a fairly popular, I don't know how popular, but a good problem, easy difficulty at least, in LeetCode called valid anagram. So the idea is to take two strings and return true if they are indeed anagrams, and false if they're not anagrams. So let's read it. Let's read the problem description. Given two strings S and T, return true if T is an anagram of S and false otherwise. An anagram is a word or phrase formed by rearranging the letters of a different word or phrase, typically using all the original letters exactly once. So as we can see here, these two are examples of anagrams because they're using the same exact letters with the same exact frequency. A appears 3 times here, A appears 3 times here, N appears once here, N appears once here, G appears once here, G appears once here. So here's another one that these two do not qualify as anagrams. We have rat and car. So rat has letters R, A, and T, but car does not have a T, but it has a C. So basically, anagrams need to have the same exact letters and the same exact frequency of each letter that it has. That's how we know two words are anagrams. So how do we solve this problem? First, let me whip out my handy dandy Google Docs. Define anagram. We'll just do S and T. It's not really our solution. So let's think about the logic here. One thing we can do is just sort the two arrays. Let's say not the two arrays, the two strings. Let's say we have rat and tar. If we sort them, and they're anagrams, and then they should be the exact same string, because two strings with the same exact letters and the same exact frequency of all those letters, well, they should be the same exact string once all those letters are sorted. So that's one way to do it. This will actually be an O n log n solution, because that's how long it takes to do sorting in Python and a lot of other popular languages. It'll take n log n time, n being in this case it'll be the number of the letters in the string, and it'll be constant space. So it's not a bad solution, but I think we can do a little bit better with the speed. We can actually do a linear speed, but we'll have to use some extra space. So how do we do that? Well, we're going to need a hash map or a dictionary in Python. So the idea is to actually add letters from one string, iterate through one of the strings, just iterate through rat in this example. Let's actually take a good example here instead of being all abstract. We want to iterate through these letters. So we have rat, we have tar. How do we know if they're anagrams? Well, we start with a rat. We add an entry for the first letter. R maps to 1. We add an entry for the second letter. A maps to 1. We add an entry for the third letter. T maps to 1. Let's add one more. Let's call it rata, and let's call this tara. So we add another A. So now what we need to do is we need to increment A, because A is actually going to be, the mapping is actually going to be the frequency of how often these letters appear. So now we have a hash map. From this hash map we know R appears once, A appears twice, T appears once. Notice we did this all in linear time. We only iterated through this string once. So that this part only takes one pass, so it's a linear time algorithm so far. But we're not done yet. So we have the hash map built for one string. Now we have to look at this other string. How can we take this string? That's the question here. How do we take this string? How can we figure out if it's an anagram of this string? Well, you need to basically make sure that the hash map you build from this string will be the same that you build from this string. Now you could just create a whole new hash map for this string and just compare each entry to this one to see if they're the same. And if that's true, then it'll be an anagram. And if that's false, then they won't be anagrams. But an easier way, faster, and in my opinion, actually easier to write, is just to loop through each letter in the string. Each time you see that letter, you decrement the frequency in this string, this hash map. And for each time you come across the letter, if you do not see that letter in this hash map, or if the hash map's letter is 0, meaning the frequency is, so let's say here, if it's 0, or if it doesn't appear in this hash map, you know that it's not an anagram. Changes back to 1. Now why if it's 0? Well, let's say we only had rat, and we would only have a as 1 over here. And when we got to this a, we would actually decrement it to 0. So when we got to this final a, we would see that it's already at 0. So that means we can't have an anagram here with just, if we were assuming this is just rat, that means Tara and rat cannot be anagrams, because Tara will have 2 a's and rat will only have 1 a. So let's take this example of rata, this made up word I created, and Tara. Let's iterate through the Tara and see what happens. So let's start with t. Decrement t. T goes from 1 to 0. So that means we're still good. It's okay if it turns to 0. So we had 1 and the frequency went down to 0. That's okay, but we should not check the frequency and see a 0. So now when we see an A, the next letter in Tara, and the next letter of the string is an A. So we decrement the value of A here. So it goes from 2 to 1. We're still good because it was 2. 2 is greater than 0. Now let's look at R. Is there an R over here? Yes. Is it greater than 0? Yes. So we're still good. We're going to decrement. All right. Now what do? We check this A. All right. Now what? Well, now we have to check one more. This is the last letter A. So A is 1. We decremented. Now we're down to 0. Now I guess one more edge case we would need is, what if this was Taran? Now how we could easily avoid this situation. Well, so I misspoke. So let's say we have Taran. So we come here. Now, how do we know, how does our logic account for this situation? Well, we come here, and we don't see an N anywhere. So we know that there's no, that it's not that they're not anagrams. But an even faster way to check this is to just check if the length of these two strings, let's call them S, call them T, had the exact same length. So in order for two strings to be anagrams, they're going to need to have the same length. They can't have two different lengths. It just wouldn't be possible because they wouldn't have the same letters and frequencies of each letter. It just wouldn't be possible. So the reason I kind of made that side track is I just wanted to show that, we could check if we have Reta and we have Taran, made up names here, sorry. We could iterate through all the letters, but we also could just check that the lengths are not the same at first. So before we even run into all this logic, we can first just quickly check if the two strings have the same length. Now let's do one more case one more example to show a negative case. So let's iterate through this first string and put each letter in a hash map with its frequency. So C maps to 1. A maps to 1. T maps to 1. So we have this hash map of 3 letters, C, A, and T, and they each have 1. Now, once again, the logic is so the idea is that this hash map we create from this string should be the same we create from this string. An easy way to check that is, like I said before, we just iterate through this string and actually decrement the values of this hash map. So now, and if for each time we look at a letter, once again, we're going to check if the letter exists in this string, in this hash map, and if that value of that letter is greater than 0. If those are both true, then we continue. If any of those two are false, we return false, and we know that we're not dealing with anagrams. So let's check A. Is A in this hash map? Yes. Let's go ahead and decrement it to 0. Alright, now let's check R. Is R in this hash map? No, it's not. So since R is not in this hash map, we can already return from this statement here, return false. So we know this is not an anagram. Okay, it's really hard to write with this, but you get the idea. These two are not anagrams, so they do not have the same letters. And as I mentioned before, we could check that they have the same length, which these two, in this case, they both do. But once we ran through the actual logic, we noticed that these are not anagrams. So how do we code this up? Go to Google Docs. Alright, let's first check if they have the same length. If length of S not equal to length of T, we return false. We know they can't be anagrams, so they have different lengths. So now we want to make a map. We can call it chars. This is gonna be a dictionary. We're gonna initialize it to an empty dictionary. What are we going to fill this dictionary with? We're gonna fill it with the letters and their frequencies of the string S. So, okay, so for char in S, chars of char equal chars.get char plus 1. So what this is doing is, this actually here is just a Python kind of syntactic sugar to find out if it already exists. We're going to return the value of the chars of char. If this doesn't exist, we're going to have a default value of 0. So we're going to insert the frequency. We're going to insert the letter if it doesn't exist. If it does exist, we're just going to increment the frequency by 1 into this map called chars. Alright, so now we have this map called chars. What are we going to do? Well, we want to iterate through the other string. The other string is T, okay? For char in T, now what do we want to check here? So we have two conditions. So the character in T must exist in this dictionary, in this hash map, and the value cannot be 0, because that would mean it would have 0 occurrences, or it's been decremented enough to have 0 occurrences already. So if char not in T, or char not in chars, or chars of char, maybe not the best name here, equals 0, return false. And what do we want to do each time? Remember, we have to decrement the value of this value in the hash map. So we want to do chars of char minus equal 1. So now, if we can get this far, we know they have the same length, and if we know they have the same exact frequency, we have the same exact hash maps, basically. They create the same exact hash maps, which we can do by creating a hash map here, and then doing the reverse, and just making sure we don't violate this condition here. We know that the two are actually anagrams, so we can actually return true in the end here. Now let's see if this works on LeetCode. Oops. Alright, let's type this in. As always, we have a disaster when it comes to formatting. should hit submit. Okay, yep. And here we go. Success. We got faster than 95%. We use memory at less than 90%. So yeah, that's, in my opinion, the easiest way to do this. Once again, we create a hash map from the first string S, and then we iterate through the next string. We decrement each value in the hash map, kind of undoing what we did to create this. And then we should end up with this this hash map full of empty values. Well, not really empty values, but hash map full of nothing but zeros. And that's the logic we can use to determine if two strings are anagrams. Alright, I think that's all we're going to do for today. This is the first time I ever did this. Last year in August. Cool, I did it in Java. Not August. Is that October? Did it in Java. But yeah. So that's a valid anagram. It's a pretty good way to exercise your string knowledge and your dictionary knowledge. It's once again, it's linear runtime. It's big O of n for speed, and big O of n for memory. Why is it big O of n for memory? Because we're using, well, actually it's going to be constant memory. I'm sorry. I take that back. So it's big O of n for speed because we're going to iterate through, iterate through just the length of the strings. But why is it big O? Why is it only constant speed? Well, because, in this case for valid anagrams, we're only working with lowercase English letters. So it actually depends on what the constraints are, but in any case, you're only going to have a constant number of possible entries in a hash map. It's only going to grow up to 26. The values can keep increasing, but that won't change the memory. But the hash map cannot grow any bigger than 26, no matter what. You can't have 27 letters in the English language. So it's actually going to be O of 1 constant space, actually. So it's going to be linear runtime and constant space. But yeah, thanks for watching, everybody. Once again, this has been the LeetCode Larry Show. I am your host, LeetCode Larry, the only guy on the planet named LeetCode Larry, whose name is not actually Larry. Ciao.